What is going on, everybody? Welcome to a bit of an old style Sentex video. A little bit ago, I released the following two animations for neural networks and kind of visualizing what is happening inside of neural networks. So I have this one showing basically the various layer outputs all the way from input all the way to the actual output confidences for this classification model. As well as another one showing the live weights changing inside the model as the model trains. I really just made these purely for visualization's sake, but people were asking how it was done. It's really just a lot of matplotlib code for the most part, but I can go ahead and just show how it's done. The code is not the greatest. It wasn't really meant for public consumption, but my code never is really that great, so I think we'll be okay. I'm going to go ahead and start with the following code already in place. Now you might be seeing this and being like, hey, what the heck? That's basically everything, isn't it? And it's really not. Basically, the way I've made these animations is with the neural networks from scratch architecture itself. So I did that because that's the one I know the best. I know the neural networks from scratch architecture, well, like from scratch. So it's like the lowest level and easiest one to truly understand. So that's what I'm going to be using here. You don't need to have anyway, you don't need to have followed along or bought the book or anything like that to follow along here, because here all we're going to be doing is just utilizing this library. So if you want to learn more about how that library actually works, go for it. But otherwise, you can treat it like you probably treat TensorFlow or PyTorch or whatever your favorite machine learning library is, which better be PyTorch. So anyways, I'm going to start with the following code. So first, this little bit of code here is going to just download that fashion MNIST dataset. And that fashion MNIST dataset, if you don't know, it's like MNIST, only rather than numbers, it's articles of clothing. So you've got t-shirts and pants and shoes and other things like bags, something like that. Anyway, it has 10 total classes, and it's just a little bit harder to learn than regular MNIST, but it's still a very easy one to learn, for a neural network model, to learn. And it's also a little more interesting because everyone just does MNIST. So it's just a tiny step above. Anyway, you can feel free to do this sort of project though with your own data, your own models, all that. This first bit of code just simply downloads that data set. So I am going to host this notebook in starting form and then in the completed form. So once I'm completely done making it, so I'll probably have one of the notebooks and then it'll say like start or something like that, and then the other notebook will be like totally complete, because I will be utilizing Copilot here as we write code. I might copy and paste some other code. And so you don't want to, I just don't want anybody freaking out thinking they got to keep up with everything that's happening. Instead, I'm just going to explain everything as I go through it. But anyways, so this little bit is like, I think 4 cells. So it's grabbing the data, then this next one. So it grabs the data, downloads it, and extracts it. Down here, this is basically all that neural networks from scratch code. Let's see if I can't get a zoom out a little bit. So here, it's basically, we've got some layer definitions, we've got dropout, activation, all that stuff. The only modification, if you have followed along, I don't know why I want to say following along. I don't know why, my brain keeps wanting to say that really bad. If you have followed along with the neural networks from scratch book or whatever, and you've made it to the end, the only things that I've added here are the training dictionary definition here, and then the actual utilization of it. So at every step of the way, we've got this training dictionary. For every epoch, we add an empty dictionary. For every step, we also add an empty dictionary. And then finally, at every step inside that empty dictionary for each layer, we have another dictionary. And then inside that dictionary, we are adding the per layer weights data, bias data, the derivatives of the weights, biases, the weight momentums, and the bias momentums. All of which are very interesting pieces of information that could be visualized. It's kind of funny. Everybody calls those, internal layers of a neural network hidden layers, and honestly, no one ever looks at them. But they're not really hidden. It's just all anybody ever cares about is that final output layer running, like loss and accuracy on that output layer. But really, there's all these other layers, and lots of stuff is going on there. And if you never actually look there, you're kind of missing out. Those layers are anything but hidden. The values are definitely there. So anyways, it's kind of a misnomer and kind of a sad thing that we call them hidden layers, and really to this day, people pay very little attention to the internals of a network. And as you'll see, this is just obviously a really basic example, but you can derive a lot of very useful insights from not just, we will be analyzing a lot of that kind of output layer, but the result of, hey, why is this output layer doing what it's doing? Like, why is the model getting confused on certain things, or which things is it confused on? It becomes really easy to tell this if you just simply pull open the hood just a little bit and look. So anyways, that's the only addition I've made is just adding this training dictionary, and then basically as the model trains, we're just grabbing these attribute values for each layer and saving them into a dictionary. That way, every time we have like a visualization idea, we don't have to retrain the model and re-grab these values as it trains. So anyway, we're going to save that, and then coming down here, I think all we do first is create and split the data. Yes, so I'll go ahead and run that cell before I forget. Okay, I guess it's only 3 cells. So then finally, this third cell is just simply defining the actual model itself. So in this case, it's going to be 2 layers, 2 hidden layers of 32 units each, and then the final output. We are going to use the atom optimizer, categorical, cross entropy for loss, because we are going to have that output of 5 samples, 10 classifications, where each value is a sort of a degree of confidence. We're going to train for 5 epochs, patch size of 128, cool. Basically, when everything's done too, we will save that training dictionary. So let's go ahead and run that and let this bad boy train. You can see already before even epoch 1 was over, we were at, 75% accuracy. By the final epoch, it looks like we're about 85, 82, 80. It gets a little wild actually at the end there. Is it done? No, still running. So while we wait on that, let me go ahead and close this. We will actually begin to potentially write some code. If you are following along, I'll do my best, but at this point, I assume, as I've evolved, I hope my viewers have somewhat evolved, but if it says you're missing a package, download the package, right? But just in case, pip 310, we will be installing tqdm, matplotlib. If you don't have matplotlib and you're watching this video, you're screwing up life. And the same thing with OpenCV-Python, honestly. The only other thing is if you are following along on Ubuntu with a notebook, and we're going to want to do both matplotlib inline, but we're also going to use TK. And I want to say on Ubuntu, it's like you got to do like an apt-get. It's like Python 3 tkinter or something like that. Google it, GPT-4 it, whatever it is you want to do, Quen it, Mixtral it, figure out what that right one is. But anyways, continuing on, there will be little things like that you'll probably have to grab and make sure you have. But anyways, okay, so we've got the model, it's trained, we can view the scrollable element, and this just gives us, I'm not even really sure what are we, oh, this is the whole oh my goodness, that's that whole training dictionary. I'm gonna regret having done that. Did we really print, oh my gosh, we do. I'm gonna get rid of that. I shouldn't have viewed the scrollable element. So I think that's just going to give us lag. So the first thing that we'll go ahead and do is we'll come down and let's just get a quick visualization of the data that we're working with. So import matplotlib.pyplot as plt. That's fine. I hit my caps lock. And then we'll just do plt.imshow, and we're just going to show x test 0. I already can't type and I just started. It's been too long since I've done an old style video apparently. Okay, so we will plt to imshow. This should show inline because we're in a notebook. Very good. It looks like a pullover or some sort of jacket, something like that. It's obviously giant. And in fact, let's make it even more giant so y'all can read my text, hopefully. Okay. Yeah. So this is our input data, and actually our input data this is a reshaped version of our input data 28 by 28. It's actually just a vector of 784 values. But anyways, not only that, we can also model.predict, and we will predict on x test 0. And anytime we do anything with this like model object, all of the model attributes are getting modified. So when we do a model.predict, we can go ahead and do the prediction, and this just outputs that output layer. And that's really all the classification models are doing, right? They're just going to output that vector of 10 values, and whichever one is the argmax is the predicted value. So we could say np.argmax, and we can just run a model.predict again. Yes. And we can see, okay, so class 2 is the predicted value. We can also go ahead and just print out what was the correct value. So y test 0, okay, the correct value was 2. Not only did we see that full output layer here, this is generally where people stop. But again, like I was just saying, you can go very deep into these models. So for example, we could go for layer in model.layers, and this little iteration here, it will, every time you do a forward pass through this model and the back pass, it is going to update the various values on that model object. So at any point, we can iterate through the layers and grab information. So I can say print layer, layer.output. We don't actually want .shape. And these are all of our outputs. And as you can see, we got 1, 2, 3, 4, 5, 6. Now you might be thinking to yourself, well, what the heck? We should have only 3 layers, right? You've got your input, then you've got your hidden, and then output. So it really, in theory, if we're excluding input layer, which is just your input data, we should only have 3 layers. Well, the reason why we have 6 is because we have the layer and then the activation of that layer, which in this case is rectified linear. So, okay, so that's why we have 6 values. But again, these are the output values of the layer and then the output values after activation, which is why in this vector here, we can see, well, really, give me this. Here, we can see there are zeros, and those zeros are replacing any instance essentially of a negative number, right? Because of that rectified linear activation function. Okay, so now what we can actually do is visualize essentially all these values. So the way we're going to do that is we are going to start off everything. The most important thing whenever you're doing matplotlib is from matplotlib, you need to import style. And the style that we almost always are going to want to use is not the one that gets recommended from your editors all the time. And instead it is actually dark background. That is the style you want to use, not 538. It always wants to use 538. So now we're going to define visualize underscore the layers. We will pass 2 parameters. It'll be sample, it could be sample, but I'm going to go sample num since that's what my notes have, and figure. Okay. So in here, we will pass the figure. The only reason I'm doing it that way, rather than like defining the figure and then just kind of like, you know, clearing it or just updating it in the function or setting it every time in the function, is eventually I want to be able to animate this or use the pause thing. And I think in both instances, but for sure with animate, you want figure to be outside. So that's all, that's coming outside for that reason. So yeah, this might do a thing, but this isn't actually where we're going. So let's just, I guess, code for ourselves for one. So input data will equal x test, and it will be the sample num. Then we're going to have output truth, or truth, whichever. Oh my gosh, truth equals y test sample num. And then finally, the actual prediction will be, yes sir, just like that. Very good. So then, we are going to change some colors based on whether or not the prediction was correct or incorrect. So if I come over here, you can already see, maybe not, those are averages. Let's go over here. So you can see here as it's predicting, sometimes it's showing red, like, hey, it got the label wrong. So that's all I'm trying to mimic now. So what we're going to say is if, and there's probably a better way, you could probably just check the prediction first before we're going to do what I'm going to do. But again, I did not write this code thinking I was going to show it off, and I'm definitely not showing it off. I am showing it though. np.argmax is correct. Oh. Man, sometimes it is pretty crazy. Copilot. That's pretty wild. That's not exactly my notes, but it's close enough. So what we're going to say is if it was correct, we're going to say title text equals, it will be an F string, and we'll say correct, prediction was something, and prediction was, and in fact, we probably want to do, we really should have saved this to a variable. Darn it. Well, really, actually, predict, let's say pred class, we'll say is that. I have to fix it. It's causing me too much pain every time. Correct prediction, predict class, truth, should be output truth, that's fine. Okay. So if that's true, color will be green. We actually don't really even need to set color. So in fact, what I'm going to say here is fig dot subtitle. Title text font size will be 14. I did font size 20. You can tinker with this as you please. I'm going to save the line and just say color equals green. Okay, so now that we have that, that's if it was correct. If it's incorrect, hopefully this will just solve the problem for me. Wrong, prediction, truth, cool. Okay, very good. So now that we've done that, looking back at the chart, we essentially have, we've got one axis here, 2, 3, 4, 5, 6, 7 total axes that we want to graph. And everything is workable to be like a vertical chart. So that's kind of what we're going to go for here next. So we are going to say AX0 will be plt.subplot2grid, and we can take the starting code here, but we're going to modify it. So because we're essentially going to do those 7 verticals, it's going to be a 1x7 grid, and then this one will start at the 0, 0 spot, and then it is going to be row span 1, col span also 1. Hey man, 1. Okay, so that's axis 0. Then we're going to do a quick speed test for Copilot and see how fast does it go. That's it's on the ball today. I love it. I love it. Keep it up. Some days it's just too slow and it would be faster for me to copy pasta. But that worked out. And Copilot is smart enough to understand that we are out of axes. This is all we want, right? Because it's a 1x7. We've filled them up. I love it. Okay, so now that we have our axes, we can actually plot to the axes. So let's, we're going to call these values what they really are. So what I'm going to say is I'm going to call this layer 1. Layer 1 is going to be equal to its model.layers 0th dot output is that layer 1. Now what do we want to do to layer 1? Well, right now that is effectively a vector, right? So if we were to graph it, it would be like a horizontal vector. What we really want to do is graph it and make it like that vertical. So to do that, we're going to use NumPy to rotate it. So np.rotate or rot, and in fact, I think it's rot 90, right? Yeah, rot 90. We want to rotate that vector. Next, how many times do we want to rotate it? Well, you might be thinking, well, to go from horizontal to vertical, we would rotate it 1 time. But actually, we need to rotate it 3 times, so effectively 270 degrees, because if we just rotate it 1 time, it's actually upside down if we rotate it at 90 degrees. So instead what we're going to do is we are going to rotate, because this is rotating counterclockwise. So if we didn't do this, you probably would never know, unless you were paying attention, like I was when I started with k equals 1, that I was paying attention to the output layer and being like, no, the correct classification was 2. This was accurate, but yet it's showing, I don't know what it would be, like 7 if it's flipped. So anyway, that's the only reason I realized this. I'm not a big brain. I just happened to realize that something was wrong. And then the axes that we want to perform this on, I believe we want this to be 0 and 1 because we're trying to rotate both the column and like both rows and columns. Okay, that's layer 1. Next, what we want to do is layer 1 activated is going to be equal to basically the exact same thing, just layer 1. All we're doing is just giving it a slightly more appropriate name that I think just makes more sense to me. So then what we're going to do is basically I'm going to let Copilot just have us, I'm just going to let Copilot do all this for us. We do have layer 3 activated. How smart is Copilot? Copilot is pretty smart. We do actually want to show that. I don't want to let it get too far in advance for us, but anyways, we do actually want it. So we set the data. Okay, we've got everything correct. Now we're going to run through. Okay, so we've got AX0. AX0 is going to show the input data reshaped, kind of like we just did above, to be honest. Then what we want to do is actually show layer 1. Layer 1 activated, and so on. So it's a little different order than I have in my notes, but I think we'll be okay. I bet Copilot will figure it out. Actually, really, AX0, I don't really think we even have it. I never did a title for AX0. Let's see if it will start doing AX1. So it does start to do AX1, but it's not quite what I want. But AX1.mshow, layer 1, CMap, that might be acceptable, but really the color mapping that I want to go with is going to be red, yellow, green for layer 1, because layer 1 could be anything from a negative to a positive. For the others, for the activated layers, so actually let's just go down one more. Cool, layer 1 activated. For these, because it's rectified linear, you can't have a negative value. So we won't actually have red, and it will instead just be yellow to green. Now, yellow to green sure looks a whole lot to me like it's more like white to yellowish to green. But anyways, I think that makes way more sense for the activated layers, which is basically this one, and the final layer output. I think that makes more sense, so that's why I went with that. But you can feel free to change the colors, be whatever the heck you want. You could go with Verdus or whatever that is. I don't even know how to pronounce that. So then, AX1, AX2, AX3, AX4, cool, we'll show those. AX5, that's fine. And AX6, that's fine. 0 axes off. That actually might look better than what I have because the axes are on. Do we want to turn the axes off? I don't actually think we want to turn the axes off. It'd be nice to turn off the x-axes potentially, but that's enough. We've done more than enough, I'd say. Okay, so that can be our function. I'm happy with that. So what I'm going to say is fig equals plt.figure fig size. We'll go with a 12 by 12. It might look a little goofy because of the the place I'm recording in, but this should be fine. Figure blah, 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 blah. Okay, so let's go ahead and run it. Visualize layers. We don't need a plt.show because we're just going to do this. Okay, yeah, that is quite large. Cool. All right, so in my thing, I did actually give titles to each one, L1 activated. We could do that if we want. It's not really totally necessary. I think you can tell what's what here, but yeah, okay, so that looks pretty good. But of course, you can see here that it's very confident. It seems like it's predicting class 2 quite well. But this is essentially very anecdotal. It's just one sample. And instead what we could do is kind of iterate through the above. So instead what I'm going to do now is I'm going to go matplotlib, and we will do tk. I will zoom in. Thank you for reminding me, person yelling at their screen. So the next thing, import OS, because we're going to save them. And then from matplotlib, we're going to import animation. I'm going to set a limit to 1,000. I don't want to go any more than 1,000 samples. And then we want to save these so we don't have to keep making them, because it does take a little bit to make them. And later, if you wanted to make cool animations, you would want to have already saved them and then use like FFmpeg or something else to compile them. So that's the directory name. If not, yep, cool, make it. Thank you. I love Copilot. I've heard good things about Cursor. One day maybe I'll try Cursor. But I just don't know why I would. So plt equals plt.figure. Okay, we'll keep it a 12 by 12. Next, we are going to animate. I is essentially the frame, but that's all right. Are you kidding me? Yes, that's basically that is what we want to do. So cool. Yeah, so we want to animate based on the frame. The frame will also serve as our sample number. Every time we animate, we want to clear the whole figure, and then we want to visualize that figure. And in fact, are we defining it? We're not, right? No. Seems a little sloppy. Something seems goofy there, but that's okay. I think we're fine because we redefine the axes every time. So I think that's fine. So fig clear, visualize layer, plt.save the figure. This is actually acceptable, but the way that I did it in my notes is I also added the actual truth in front. So later you could go back and inspect, I suppose, the ones that aren't accurate. Cool. Okay, so once we've done that, we can actually run the animation. So that's just animation.funcAnimation. Yes, figure, animate the frames. How many frames do we want to do? We just set the limit. Interval at 100. In fact, I would just probably go with whatever the heck the default interval is, honestly. And that's good. So then we just need a plt.show. Yep. Whew, too good. And we can go ahead and run it. So here we have our, it's just iterating through the sample. So as you can see, it's not the fastest thing in the world, which is why it could be convenient to go ahead and save them. But one thing that we can already see is you have like 2, 4, and 6 seem to be often misclassified, and then whatever the heck we just saw was all over the charts. So it is clear that despite such a high accuracy for this model, at least this particular class seems to have some confusion, at least some of the time, that it clearly is a trend to often predict 2, 4, or 6 for class 2. And so you could probably guess that 4 and 6 also often classify as 2 and possibly the other one of 6 or 4. So we can then start digging into that. And then once we dig into that, we could also be looking at the internal layers kind of from there. So that is kind of the next thing that I really want to do is actually save, rather than going sample by sample, what if we just look at the average for the entire sample truth, let's say. And I think that will bring a little more attention to what are the common mispredictions, but then also what's happening internally in that model. Like, are there actual differences? At what point in the layers are things going awry? And this can help to inform, maybe we need more layers, maybe we need bigger layers, maybe we need smaller layers sometimes. So it just really depends, because if your model is too big, it's just going to overfit to all your samples, for example. And then from there, you could also be paying attention to the changes in these values, how active is it, and then especially on like weights, for example, that can kind of tell you too when the model's kind of done training. But anyways, let's go ahead and close this out. And let's go ahead and, instead of what we're doing going sample by sample, let's go for an entire average. So I'm going to, from tqdm, import tqdm, and then we will do layer data by class. And this is going to store all of the classes of potential truths. And then each truth will have another dictionary of each class and all the predictions. Did it just suggest that? Yeah. That's basically what I want, but instead of going all the way to 9, so I guess it's not the most perfect, we actually only want to go to 5. And the reason for this is, so this is sample. So for a sample type or sample class of 0, we want to get layer 1, essentially, or the 0th layer, 1st, 2nd, 3rd, 4th, 5th, right? So all 6 layers. We want to get for every single sample, every single layer. And then later we can average every single layer to get average values. So that's what we want to do for class 0. And then we just basically want to do the same thing for class 1, 2. I'm not sure why it ended there. Why would it think that it should end there? That's kind of weird. We want sample 3, 4. What happened? We'll figure something out here. 5. Use. Oh, there's no comma. I see. Okay. Well, I thought we were saving time. We are not saving time. Okay, so 5, and then 6, 7, 8, 9, and then finally we will fully close off this dictionary. Okay, I think that's how we want it. Okay, so now what we want to do is we want to run through all of our testing data and start populating that dictionary. So for data n, so data number, in tq, or data, tqdm, range, len, x test. So this is basically just going to be, why are you so ugly? What happened? Did I screw something up here? Why I used x test? Oh, text. Woo! Oh no, tried it again. Okay, so for that data number, we are going to, essentially we want to do, we actually don't need it. We just need to run a predict. So model.predict, because again, as soon as you do the predict, it's modifying all those attributes. So we can actually just run the prediction. And then we can grab, I actually don't know that we need, no, we actually, of course we need the truth. God, stupid. The truth will be ytest data n. Then what we want to do is start adding all of the layer data to whichever class it's supposed to be. We want to populate basically all of these for every sample. So to do that, we are going to layer data by class, and then it will be truth, and then yes, the layer, so 0th, and then we want to append model.layers, that 0th layer, and that output. I believe that is what we want. Whew. Okay, so then we'll do the same thing. Yes, cool. All the way down. Come on. Why does it keep wanting to stop at 2? Oh no, this is also wrong. Ooh. So this is why you don't have messy code. So for in my head, I'm thinking this is for every class, right? But this is not for every class because you're really only, like, you're not doing this for every class. It's for every data. You figure out what the truth is, and then all we want to do is basically layer data by class truth, whatever that truth is, and then we want to save every layer, right? So we have these 5 layers. We want to save essentially this information. And this is probably why doing a loop instead of this makes a little more sense. So maybe for number of layers or something like that would probably work a little better than what I've done here. But anyway, let's go ahead and fix this, 3, 4, and 5. So again, for given a specific truth, we're going to access whatever that truth class was. Given that class, we then want to populate and append the vector of values for that particular layer. And that's going to be the output layer and then also the activated output layer. And that's why we have 6 of them. Okay, once we've done that, let's go ahead. Yeah, let's go ahead and run that and just make sure. Okay, cool. It runs. That's good. Good start. And now what we want to do is actually average this layer data by class average. So I actually want to say layer data by class averages, and that's going to be equal to really the exact same thing. Yeah, this. Yes. And then what we want to do is for class n in range, we already know we have 10, so we'll just do that. And then for layer n in range 6, because we have 6 different layers, what we want to do is calculate the average. So layer data by class averages, class n, layer n, I'm going to go ahead and accept it, equals np.mean, and we want to run the mean of the layer data. Yes, layer data by class, class n, layer n, yes. And we want to do that on axis 0, yes, which is the row. And yes, I think that's everything. So now we will have all the averages, hopefully. We'll see. We'll find out really quick. So now what we want to do is graph the averages. So I'm going to go back to matplotlib inline. Thank you. And we are going to well, actually, I think we have really everything we need. I don't think we actually have to import anything anymore. So dname, we'll call it class underscore averages. Cool. And then we'll go ahead and make that path just in case. We will use, let's see, so class. There's also probably a much better way to do what I'm about to do, but we'll go ahead and set the figure as well. Fig equals, cool, 12 by 12. Class sample dict. There's got to be a better way. Someone comment below the superior way. And class sample dict. So this will just be an empty list, I suppose. 0, 1, hopefully you'll finish for me, all the way up to class 9. So right now this is just an empty dictionary with each class, and then what we want to do is actually set it. So we're going to say class sample dict 0, and then here we are going to, we won't append, we're just going to reset it. So equals x test, and for example, we'll do this 3328. And I think I might just copy and paste these. Paste. So what is going on here? All I'm doing is grabbing a representative sample of each classification. So for a 0, I'm grabbing this, and like the class 2, for example, they're all in like order 2. So 0 by thousands, right? There's 10,000 samples, and every 1,000 is a new classification. For some reason, it doesn't go 0, 1, 2, 3, 4, through 9. It starts at like samples 0 to 999 are class 2, for example. So, and that's why, you know, the prediction and ground truth for x test 0 is actually a 2 and not a 0. Anyway, okay, so once we have that, we also, I'm going to copy and paste this as well. It's only going to be for writing. You don't really actually need to copy and paste this. And then even for these, you can just put a random sample if you want. So class description dict, basically this is just the actual text description for each classification. So 0 is t-shirt top, 1 is a trouser, 2 is a pullover, 3 is a dress coat, and so on. Okay, so once we have those, we are ready to basically graph every single one of these, their averages. So for class N in range 10, we want to graph each of these. So fig.clear, we'll probably clear at the end. And in fact, I think we'll do the figure. I don't actually know. Well, whatever. At least in my notes, I'm redefining it down here. And so I'll just redefine it again. We're not going to do that yet. And fig.subtitle is going to be average values for class, and it will be whatever that class N is. And then in parentheses, we'll put the class description dict for class N. Okay, cool. So that'll be our subtitle. Next, we want to have those exact same axes. So I'm actually just going to go copy post, copy, make some more space here. Tab over, paste those. Very good. All right. Then what we want to do is really copy and paste all that other previous data too. Ugh. And then we'll just change the values, because the values will change to be the averages, but otherwise, we'll just copy this, come back down here, paste. Very good. So rather than model.layers, it's going to be layer data by class averages. So layer data by class averages, and then class N. So class N, and then the value that we want to graph, and then it won't be .output, it's just whatever, because we didn't save it as an object. So now it's basically this replaces this, and this becomes a 1, and then replaces this. This becomes a 2. It's going to be a miracle if I get away with this. 3, 4, and 5. Cool. Okay, AX show, it won't be input data, it will be class sample dict. It will be, class N, and then reshape 20 by 28, CMap gray, very good. Off, very good. And then we'll actually go ahead and plt.save fig. We will save it to, did we actually not do? We didn't. So dname class averages. So it is actually making that. Why did it? Okay, so we're fine. Class N, and in fact, let's just save it as class N.png. .png. Cool. Okay, so now that we've done that, I think it should graph all of these for us right below it. Let's see if we get an error. Oh, it's actually going to work? Oh my goodness. Oh my goodness, it's incredible. Oh my Lord. How wonderful. Very cool. Okay, so we can see here, by getting the averages, we can see that, for example, class 0, a t-shirt, often misclassifies as a 3, which I think is a dress, if I recall right, I can't remember, or a 6. We can then see for trouser that, nope, the model is definitely very confident almost all the time about trousers. Class 2 pullover, we can see a faint 0, mostly 2, which is the right one, but also a lot of 4, a lot of 6. We get to the dress, which is, that 3, so dress is getting confused sometimes with a shirt, for example. Coming down to class 4, a coat, very confused about a 2 a lot, 6, sometimes a 3 even. And continuing along, we can see here probably class 6 shirt is potentially the worst one we've seen yet, where it's all over the place. Yeah, you get the idea. Bag, very confident. Ankle boot, pretty confident. Then what we could do is even come over to let's say one of the ones that is like frequently wrong, like 6. Let's look at 6 and 4. So if we pull up the image of 6 and 4, we can kind of see that there are a lot of similarities at like after the second hidden layer, for example. So after the second activated hidden layer, it is very, very similar, right? As opposed to like if we just switch to sandal, for example, you can see how much variance there is from class 4 to class 5 on that second layer, second activated layer. And then also coming back to 2, for example. So 2 versus 6 again, looking back at 6, we can see that really that output layer pre-activation looks unbelievably similar. I mean, really the only difference glaringly, really, I just don't see that many at all. Like this one is a little darker over here. But yeah, you can see there's so much similarity there. And it's interesting because actually the activated first layer, there are quite a lot more differences, but as it goes through the model, it definitely comes together pretty significantly. But even here, not too many differences. Anyways, interesting. But at the same time, you might think, oh, okay, well, that's obvious. Okay, so we sort of have identified a problem. But then also, I mean, just look at these. A pullover versus apparently a shirt. If you asked me to identify which of these is a pullover and which of those is a shirt, I would be frustrated. Come on. I mean, come on. So anyways, no doubt that, it's like, is the model messed up or is the samples silly? But we also know that it predicts, like class 6 predicts as a 0 sometimes. So after we get done throwing our mouse around. This one's a little more clear, like it really shouldn't be confused for a pullover or a shirt, but a t-shirt is in theory a shirt, right? So again, it might, maybe it's some of the other samples it gets confused with potentially. What else do we have here? A 4, right? A coat. Again, I mean, these are so close. Yeah. Okay. Anyway, poor models. Okay, so with the actual weights from a frozen trained model, there's still a lot of stuff that we could show. You could show the variance between samples and figure out which of the neurons is still the most active between sample given a specific classification, stuff like that. There's lots of cool things that you could still do from here. But let's go ahead and jump to the next one, which is the live updating of weights, which is actually kind of cool to see. Although with such a simple problem like this, it's over before you know it, but that's okay. Let's go ahead and make sure we're back on TK, matplotlib Wow, it already knew that's what I guess it makes sense that I'm flipping between them, but anyway, that's cool that it knows that. We are going to import pickle. We probably already have pickle because we saved it as a pickle, right? And then we also have style, which is necessary, and we have PLT already. So really, we have all this stuff. I don't even think I need pickle. So we're going to define a new function. We're going to call it make_plots. And in this one, what we're going to say is with open, and we are going to open traindict.pkl as RB, cool. And then we will set traindict is equal to pickle.load that file. Now we want to have our plots. So we are going to first set our figure. This is going to be plt.figure. We'll go with a 12. Well, in my notes I have a 15 by 5, but I think I actually ended up changing it somewhere as well. I think it gets like redefined. No, maybe not. Okay, well, the more you know. Don't even know my own code. Okay, 15.5, sure, we'll just leave that there. And now we're going to define 3 axes because again, in this chart, where is my, I think it's this one. Yes? Yes, right? In a sense, we want 3 graphs on this figure. 1, 2, 3. So I'm actually going to use the more basic way of making figures, and that will be ax0 equals fig.add subplot, and it's going to be a 1 by 3, and this will be plot number 1, and then we'll do it 2 more times. So bang, bang, 1, 2, and this will be plot number 2, plot number 3. Then there's probably a better way to know this, but I'm just going to say we know there are 5 epochs, 4 epoch in range of epochs, but traindict, we actually saved the epoch number. So I actually want to say range 1 to epochs plus 1. Then, oh, yeah, this is all goofy. I mean, maybe that would be cool, right? Because we have our training dictionary. PLT.pause. Where does it, oh, it clears here. Let's just look at what that shows. I'm curious, actually, so. I think we actually have to PLT.show like here, probably, right? Matplotlib, yeah, TK. So PLT.show. Let's just see what happens. I don't think that might not run, but oh, that is kind of cool. That's messy as heck, but kind of neat looking, I suppose. Yeah, okay, sure. Bye. Uh-oh, we never live that one down. I hope I get away with that. Okay, so let's get back to what we were trying to do. So PLT.pause, legend, I don't know. For step in range are, is that really what I want to do? First step in, oh man. I broke my brain. Okay, okay, so for epoch, let's go ahead and print epoch, where we're at basically. And then for step in train dict that particular epoch, what do we want to do? Well, we could print, or we could make a graph for every single step. But I propose that we don't do that because step to step, the variance is pretty minimal. So we can actually do things a little quicker, a little more seamlessly if we don't graph every single step, because it's a little unnecessary. If you saved every single chart and then you later put them together again with like FFmpeg or something like that, then sure, go have at it. But otherwise, it'll just be too slow, I think, if we do for every single step. So instead, what I'm going to say is if step modulo 10 equals 0, then what we will do is we'll print the step. And in fact, let's print step. Cool. So if that is the case, now we want to graph it. So what we're going to say is weights underscore 0 equals train dict epoch step 0 weights. Yes. So we're just accessing that training dictionary, and then we're going to do this for weight 0, 1, and 2, 1, and 2. Cool. Now we want to show these, so we're going to say ax0.imshow weights 0. CMAP will be red, yellow, green. Red, yellow, green. Beautiful. And then we want to do that, whoops, we want to do that for pasta. 1, 2, 1, 2. Very good. And then we will fig dot supertitle fashion mnist densenet epoch. What is it? Just epoch, right? Yeah, epoch. Step. Cool. Oh, yeah, we'll set the font size too. I'll take that. Font size 20. Cool. Whew. All right. So now we can. We could give a little description just in case anybody's not fully following along. Set title. This first one will be layer 1 weights. This takes in 784, out 32. AX1, layer 2, in 32, out 32, and oh my gosh. That's pretty impressive. Okay, very good. I also set it, I did set the font size, so AX0 title dot set font size 10. So I did set these a little smaller, so I'm going to go ahead and copy, paste, 1 and 2. Cool. For some reason, I can't remember if it's just, I think it's just to stretch so things didn't look a little goofy. So basically I wanted these all to be approximately as wide as each other, irregardless, Irregardless is not an acceptable word, regardless of how wide or how many, because like here we've got quite a few values versus here versus here. Well, really, actually, this is 32, this is 32, this is only 10. So anyways, continuing on. So I did set that, so let's go ahead and ax0.set underscore aspect to, I went with 0.05. Again, that's just to stretch axis 0. I'm not really sure. I guess I'm trying to decide why. Maybe because they were trying to be the same size as the y-axes. Maybe that's what it was. Anyway, continuing along. So ax0.set underscore ylim. We're 0 to 784, so it doesn't show any negative values there. And then fig.set size inches. We'll go 8 by 8. Again, this was just in my notes. This is probably only for like since I was saving the figure. But anyway, now we will use plt.pause indeed. This is a nice short pause. And then finally, we need to clear the axes. So ax0.clear, ax1.clear, ax2.clear. Then we run a plt.show and we can make plots. And let me see. I don't think we have anything else. So this should show the changes over time. Let me go ahead and run this really quick. So actually you can already see it started when I wasn't able to show it, like I couldn't show it so quick. So really in that, all the action pretty much happens in that first epoch, and then from 2 to 5, very subtle changes are happening. It's very hard to see anything really in real time changing, which is why if we come over to the Twitter post, you'll actually see that we start on epoch 1, show it quite heavily, but then as soon as we jump to epoch 2, I basically go, I super speed up epoch 2 to 5. Like 2 to 5 is like a snap of a finger speed, because you can see how very little is changing. Here's epoch 2, and then boom, like such minimal changes. Tons is happening in epoch 1, but then towards the end, very, very little is happening. So anyways, thank you. So anyways, those are the 2 animations, very long video, but hopefully some of you found that interesting and have enjoyed the slight return to the more old style videos. Anyway, pretty cool. I feel like there's so much that can be visualized here. So if you guys have any other ideas of like things that can be visualized, like make a new file and then like a pull request or something on the repo that I'll link below with the starting code and the finished code for at least up to this point. I'd love to see what other people can come up with. I feel like there's so many cool visualizations that can be made when you have such an obvious how it works neural network kind of framework. And again, if you don't have to have known neural networks from scratch, but if you want to learn more about all this code and exactly how everything works, how all the math works, all that, check out the Neural Networks from Scratch book at nnfs.io. Otherwise, I will see you all in another video.